Hey, and welcome back to DATQVAULT video lectures. This is one of two lectures on elimination reactions to form alkenes. Elimination reactions go by this type of mechanism right here, where you have some sort of a leaving group and a hydrogen alpha to it, and based on the catalyst that you use, you can get an elimination of these two things to form an alkene. This lecture we're going to focus on the dehydrohalogenation reaction to form alkenes, where the leaving group is some sort of a halogen, where X equals halogen. And this reaction is promoted by a base. So the basic mechanism for a dehydrohalogenation requires some sort of a strong non-nucleophilic base. Bases that are usually used for dehydrohalogenations are some sort of an alkoxide salt, where sodium and oxygen are your salt pair, and R equals some sort of a long hydrocarbon chain. So this oxygen is extremely basic, so it's going to deprotonate this hydrogen here, alpha to the bromine, or any kind of halogen leaving group, and then the bromine is going to get eliminated. Once this reaction happens, we're going to end up with our alkene. We're going to end up with an alcohol as a byproduct, and we're also going to end up with sodium bromide as a byproduct from the sodium here in the base and also the bromide that leaves. Dehydrohalogenation reactions, which is important to know, they're always an E2 elimination reaction when done in the presence of a strong base. The halogen never leaves to form a carbocation, so if you remember, E2 elimination reactions are concerted mechanisms, and they go without the formation of a carbocation intermediate. So as I said, bases are extremely important in dehydrohalogenation reaction, and because of this, it's important to use the correct base when doing an elimination of this type. Bases that are usually used for primary halides are sterically bulky, strong bases. So we use a base such as this tert-butyl alkoxide. This is because if we used a smaller base or a smaller alkoxide, we would probably just get a substitution reaction with the chlorine to form an ether instead. But due to this base being extremely large, it actually can't get in here to this carbon to do a displacement. So instead, it just deprotonates the alpha hydrogen and does an elimination reaction to form our alkene. When we have halogens that are more sterically hindered, like this halogen here, this secondary halogen, so secondary and tertiary halogens, you can use smaller, not quite as bulky bases, because the carbon right here is actually sterically hindered. So the base actually can't get in there to do the displacement. So again, it's going to do the elimination reaction instead. It's important to remember when doing eliminations to form internal alkenes that we're going to get a mixture of the cis and trans isomers. So here we have the trans alkene or the Z alkene, and here we have the cis alkene or the E alkene. In this reaction, the major product is going to be the Z alkene because it's more thermodynamically stable than the E alkene. So it's important to remember to use Zaitsev's rule when doing any kind of an elimination reaction, including dehydrohalogenations. Zaitsev's rule tells us that we're going to eliminate the hydrogen off of the substrate that is going to give us an alkene with the highest number of substitution. So if we eliminated this hydrogen down here, we would get this alkene, but this one's not going to be eliminated because we're going to eliminate this hydrogen instead, because we're going to get a more highly substituted tri-substituted alkene versus a disubstituted alkene. So this is going to be our major product. So remember to use Zaitsev's rule. Remember, when you have more than one option for eliminating a hydrogen, you're always going to eliminate the hydrogen that gives you the most substituted alkene. All right, let's do a question really fast. So in this question, we're asked to draw all the possible products for the following elimination reaction, and then it's asking us to circle the major product in this reaction. So why don't you go ahead and pause the video and take a second and solve this problem, and then we'll come back and solve it together. All right, so this is of course a basic elimination reaction. Notice that we're using a smaller base. That's because we have a secondary halide, so we don't need to use a large sterically hindered base because our halide is already sterically hindered. So there are one of two hydrogens that we can actually eliminate to form an alkene. If we eliminate the hydrogen here on the right hand side, we're going to get this terminal alkene. If we eliminate the hydrogen at the internal position, we're going to get one of two products. We're going to get this internal alkene, or we can actually get the other isomer of the internal alkene. This being our Z isomer, this being our E isomer, and this being our Z isomer. Alright, so if we remember, we're going to form the E isomer instead because it's more stable thermodynamically, so this is going to be our major product. And then, of course, our minor product is going to be over here because it's the monosubstituted product. So first and foremost, we want to follow Zaitsev's rule, and then if we are forming an internal alkene, we want it to be the transalkene. Alright, so dehydrohalogenation can go with base, but there are also some dehydrohalogenations that can go in the absence of base. If you do a dehydrohalogenation in the absence of base, it has to be a tertiary bromide or a tertiary halogen of some kind. This is because following an E1 elimination pathway, if the bromine leaves first and we don't have a base to actually pull off a proton, we're going to need to be able to form a very stable carbocation intermediate. If we have a tertiary halogen, we're going to form a tertiary carbocation, which is very stable. So this reaction will actually go just by using heat. After we heat this up and form the carbocation, the bromine will actually come in and eliminate the hydrogen, and then we're going to form our alkene. So the bromide in this case that leaves initially to form the carbocation is then going to act as our base to do the elimination of the hydrogen to form the alkene. Alright, so dehydrohalogenations were relatively simple reactions, but there are a couple things that we need to remember when doing dehydrohalogenations. We do them in the presence of base, and if we do them in the presence of base, then they always go by an E2 elimination pathway. They never go through a carbocation intermediate in the presence of base. Primary halides require large, bulky bases, and this is to avoid substitution reactions. And then sterically hindered halides require smaller bases to do the deprotonation, and a sterically hindered halide will not go under a substitution mechanism because it's, of course, too sterically hindered, and the smaller base can't get in there to do a displacement, so it in turn will just do an elimination reaction. And then also, we can actually go through an E1 elimination pathway, but we can only go through this pathway using tertiary halides, and this reaction has to be heated. We can go through an E1 elimination pathway with tertiary halides because we form a very stable tertiary carbocation. Alright, so like I said in the beginning, this is one of two elimination lectures. The other one is just going to be about dehydration, so I suggest listening to that lecture and then going through and solving a bunch of test questions based on elimination reactions.